Hello, everyone. I hope you're healthy and well. Thank you for joining us for the next talk in our Golden Webinars in Astrophysics series. My name is Thomas Puzia. I'm a faculty member at the Institute of Astrophysics of Pontificia Universidad Católica and the head of outreach activities at the Institute. And together with Evelyn Johnston, one of our postdoctoral fellows, we will keep organizing this series of talks for you for as long as we can. First of all, we would like to thank you all for the overwhelming response and encouragement from our last talks of this series. We really appreciate your comments and suggestions, so please keep them coming. We will continue to bring you these talks in the original English and simultaneous Spanish translation without any registration fees. This has been made possible by the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym. Our talk this week will be given by William Borucki, who was a scientist at the NASA Ames Research Center before he retired in 2015, and who was the principal investigator of the Kepler Space Mission. First, though, we will give a brief introduction of how the webinar will run.
I'm sure many of you know how we're going to run it now. We have arranged for simultaneous language interpretation provided by Mr. Patricio Gonzalez, Director of Serendipia Soluciones, who will be simultaneously translating for us in both the English to Spanish and Spanish to English directions. On your devices, you can switch between the English and Spanish channels using the interpretation button at the bottom of your Zoom window. Unfortunately, the live interpretation option is not offered for people using Zoom in the browser or on Linux machines. We apologize for this, but we will post both the English and Spanish versions of the talk on the Astrofísica UC YouTube channels very, very soon. We've also heard from a few participants that they could not mute the original soundtrack when listening to the Spanish translation. This appears to be a bug in Zoom, and we've been told that by leaving and rejoining the webinar should fix the issue. If you have any questions in the talk, please type them into the Q&A window. All viewers will be able to upvote questions and comment on them, and we have a team of astronomers and journalists behind the scenes who will be monitoring your questions and will select the best questions for the discussion after the talk. The talk is expected to last for around 55 minutes, and we will have time for questions at the end. The questions from the audience will be selected only from the Q&A window, and unfortunately not from those watching the live stream on YouTube.
So before we begin, we would like to introduce briefly our panel members that are with us today. So of course, William, our speaker, Patricia Gonzalez, our interpreter, Evelyn, and myself, the co-hosts. We have also my colleague, professor at the Institute of Astronomy and Astrophysics, Viviana Guzman. And we have our students and postdocs, Antonia Seifert, who is a visiting student at the Institute from Heidelberg University, and postdocs Maria Paola Ronco and Melissa Hobson and Giuseppe De Ani. We have also the great pleasure to welcome as our guest panelist today, Gordon Walker, who was a professor emeritus at the University of British Columbia and who designed the science payload for the MOST astroseismology mission. We have also with us James Hesser, the Director Emeritus of the Herzberg Institute of Astrophysics in Victoria of the National Research Council of Canada, and Christian Maroa, who is a research officer also at the National Research Council of Canada, Herzberg Institute of Astrophysics, and the first person to image actually the multi-exoplanetary system directly. So maybe you've heard of HR 8799. And with us today is also Christian Gippone, who is a faculty at the Astronomical Observatory of Cordoba and adjunct scientist at the Institute for Theoretical and Experimental Astronomy in Cordoba. And we have also with us today our Q&A managers, Carol Rojas, Daniela Fernandez, and Ricardo Acevedo, who will be sifting through the questions and comments from you in the Q&A window. So let's introduce our speaker. It is our great pleasure to introduce William Borucki as our speaker of the Golden Webinar this week. William's career started by studying physics at the University of Wisconsin in Madison, where he received a master's degree in 1962. Following his degree, William moved to NASA, where he worked on laboratory and theoretical studies of the radiation environment of vehicles re-entering Earth's atmosphere. Ultimately, his research led to the design of the heat shields used by the Apollo space program, which protected the spacecraft and their occupants, of course, from being destroyed by heat upon the re-entry into the atmosphere. So very important tasks. After his work for the Apollo program, he studied meteorology at the San Jose State University, where he received another master's degree in 1982. This work led to his research at NASA into the nature of lightning, both on Earth and other planets in the solar system, and the study of how macromolecules can be formed in these lightning conditions.
In 1984, William started searching for transiting extrasolar planets, which involves looking for a periodic dimming of in the light of the star caused by a planet passing in front of it and blocking some of its light. This work led to him being named the chief investigator for the Kepler Space Telescope, which was launched in March 2009 and so far has detected 2,662 planets orbiting other stars during its nine-year mission. He held this post up to his retirement in 2015. For his work, he's received many awards, including the Henry Draper Medal in 2013 from the United States National Academy of Sciences, and in 2015, the Shaw Prize for Astronomy for his conceiving and leading of the Kepler mission, which greatly advanced knowledge of both extrasolar planetary systems and stellar interiors. And now we'd like to hand over to William to tell us about his work on the Kepler mission.
Thank you very much. I'm honored to be here and speak with everyone. I'm going to start with a little discussion of the Kepler mission and then go on and talk a smidgen about my career. I think although it's been explained very nicely. Basically, the Kepler Space Mission was conceived as an attempt to find out how mankind might move in the galaxy and determine is there other life out there. To do that, the first thing you need to know is, are there other planets out there? The answer is no. If our own planetary system is unique, there probably is no life throughout the galaxy. Clearly, what we have found is the opposite. In fact, there's many, many planets around other stars. But the mission was designed as a probe, Discovery-class mission, find out Are there other planets out there? Find out if they're common or rare. Give us the statistics we need, the science community, engineering community needs to plan much more capable missions, rather than just a probe mission, but to look at planets and say, does that planet have an atmosphere? Does it have any signs of life? And so I'll talk a little bit about that, but I'm going to start out talking a little bit about my career. If I can get to move on next slide. Basically, as was mentioned, 1962, I finished a Master Science degree at the University of Wisconsin-Madison. I negotiated a job with NASA because I wanted to work on the space missions. In particular, at that time, the Mercury and Gemini missions were either finished or underway. I had a chance to work on the Apollo mission, which was the first mission that would take us to the moon and return. So I joined the team to help develop a stable spacecraft. That's important because the spacecraft has more than one equilibrium position, in which case, if it goes to the second one, it's likely to kill the astronauts. And to develop the heat shield for Apollo. The heat shields are critical because, of course, the temperature outside the heat shield is excess of that of the sun. It's like taking the space capsule and sticking it into the surface of the sun and seeing if you can cook the astronauts. The trick is not to do that. I joined the team, and I like to call them a can-do team. Basically, when we were faced with all sorts of difficulties, nobody had ever done this or hadn't done that, we found ways to do it. It was a can-do. We can do it. Let's find out how to do it. The work that I did had to do with spectral and photometric analysis of the radiation from the plasma that surrounds the heat shield as the spacecraft enters the Earth's atmosphere. And I'll talk about that a little bit later. Clearly, the mission was successful. We got to the moon, returned our astronauts safely. And of course, at the end of that, basically our team was fired. That's usually the case, in fact, most teams that work on space systems. If they're successful, they're fired and told to go find another job because that task is over. So I did that, of course, and joined another team at Ames where we looked at the Earth's atmosphere and how it was being changed by pollutants. In particular, the change that we were interested in is how the ozone layer around not just the Antarctic, but throughout the planet was being decreased by the pollutants we were emitting. During that period, after 1907, I also looked at lightning activity in planetary atmospheres. That's important for several different reasons. The most obvious one, of course, is that when lightning occurs in the Earth's atmosphere, it takes the nitrogen and oxygen molecules, recombines them to form nitric oxides, adds some water vapor, and forms fixed nitrogen. Fixed nitrogen, of course, is what's required to evolve life on Earth. And of course, it itself could actually be forming pre-biological molecules, both in the Earth's atmosphere in the past and in other planetary atmospheres currently. In 1983, I began to develop and advocate a multi-star photometer that had enough precision to find Earth-sized planets. At that time, people had a number of other approaches, but I felt the transit method was the best method to find small Earth-sized planets in a habitable zone of other stars. After a number of years of building prototype systems, working with a number of other groups, National Bureau of Standards, for example, I began writing proposals for the development of the Kepler Space Mission. After 2 years, you had an opportunity to write such a proposal. We wrote one in 1992, 94, 96, 98, and finally was accepted in 2000. 2001 started the development of the Kepler mission, launched in 2009. 4 years later, the prime mission was finished, and we now knew that there were more planets than there were stars in our sky. 2 years later, I retired and became an associate, where I document some of the Kepler history, and basically I'm a volunteer there, so that's really my prime task, although I've been writing some papers as well. So let's go on. Chloe and I talked about the fact that I joined this can-do team on the Apollo mission. It's absolutely critical that when you build a spacecraft, you launch it, they fly to the moon, they come back, they don't die on the entry. It's just absolutely critical. And the only way you can do that is to build a system in the laboratory where you can fly models with the correct materials, with the correct velocities and the correct heating levels, so that you know for a fact the heat shield is going to be perfectly satisfactory and they will get through safely. This is our facility. We're going to have to fire a model, not at orbital velocity, but escape velocity, much, much higher than orbital velocity. We're going to do that by firing air, massive air through the system, through this test section. And as it flies through there at supersonic velocities, we're going to fire a gun. And that gun is going to fire a model through that airstream. And the total velocity will be that of lunar speed when you fall 384,000 kilometers and hit the Earth's atmosphere. Two naval cannons bolted together, they fire into each other, they compress the air, the air goes through a supersonic nozzle, goes to the test section, we make our measurements here. And this is, as I say, is the gun. The gun is 145, well, that would be about 50 meters long. This is a picture of this test section. Test section has 16 windows along the side, and it's dark inside. But if you look in the windows, you see it's light inside. That's the light from this little model traveling down here, brighter than the sun, illuminating everything in its path. These are the cameras, the 16 cameras that take pictures. Pictures, generally exposure times of the order of a microsecond, and your timing had better be that good as well. And then here on top are another 16 cameras getting orthogonal views. I'll tell you a little bit more about them shortly. If you put a camera inside the test chamber, as was done here, you can see the muzzle blast from the gun, and you see the model shooting out ahead of it. The model has this little white spot. It's material hotter than the surface of the sun. This is the heat shield being burned away. The material, as it burns, flows behind it and glows and produces heat as well. And it trails the system. So you actually have a heat shield in front and in back. If we look at the cameras don't take pictures. The cameras take shadowgraphs, which means they shine parallel light through those windows and they show you what the shadow looks like. And here's our model. The model has got this very strong shock wave. It's just traveling at Mach 50 through the atmosphere. You can see the surface boiling off, it's burning, and the burning material is flowing around the sides and flowing into the wake behind it that then radiates to the back of the spacecraft, as well as, of course, the extremely hot plasma here in front of the spacecraft. Yeah, we don't want to do that. I talked about the fact that lighting is important in our planetary system, including on the Earth, although certainly with the systems that now produce fertilizer, the lighting is nowhere near as important in producing fixed nitrogen. But here's Jupiter. Jupiter, of course, always has a bright side facing us, so this is clearly a picture from a spacecraft that's gone beyond Jupiter and is looking back at Jupiter. It's a gas planet, so putting this latitude-longitude grid on was quite a trick. There's no fixed features on Jupiter other than the magnetic field that we fixed to. Along 55 North, we can see brilliant lightning storms here, right at this latitude, and a little bit here north of that, another little group here. The circulation patterns and the winds in Jupiter are very, very different than Earth. These lightning flashes, of course, are extremely far away, and they're as bright as the brightest flashes from lightning on Earth, the superstorms. In fact, they're so bright that people who study them are generally military people who are looking for bright flashes like that from thermonuclear weapons tests. So they're very bright. We also have lightning on Venus, but that's much more controversial. Even centuries ago, people would look at Venus and they would notice that as Venus came between the Earth and the Sun. It was, you see this dark area on Venus, the backside of Venus, but that seemed to glow. It was called the ashen glow, and for a long time, people thought it might be due to lightning flashes on Venus, and certainly the Russian entry probes believed they saw lightning events. I wasn't so sure that was the case, and so I put an experiment aboard the Venus orbiter, Pioneer Venus orbiter, and looked for lightning flashes. I didn't see any, but what I saw in these regions, these that I've shown here, are glows. This is the glow that might very well have given rise to the ashen glow. And the glow occurs not because of lightning flashes, but because on the bright side of Venus, the ultraviolet light from the sun disassembles the molecules, dissociates them, and forms excited carbon monoxide and carbon dioxide and other molecules. And they move with the wind, the supersonic wind that comes around the upper stratosphere, mesosphere, recombines in the dark side of Venus and forms these glows. So I don't know whether there's lightning on Venus. There's every reason to believe there isn't, every reason to believe there is. And so it's quite a controversy and certainly something that people will want to explore in the future. Now, when you know there's lightning on these planets, what you'd like to be able to do is interpret what you see in a quantitative fashion. So you need to say, well, on Jupiter, I see these bright lightning flashes. I can make some calculation of how bright they are. But I need to know how much energy went into making that lightning flash. I know full well that most of that energy did not come out as light. It came out as heat and shock waves. And it's that heat and shock waves that made the pre-biological molecules and did the formation of nitrogen. So we're going to have to do that in the lab. Here's a powerful pulse laser, comes through a lens, the lens focuses into a dot. You can assume that there's no such things as photons, for instance, only waves. And if the waves, that's true, all the energy is carried by a wave, then its electric field must instantaneously reach extreme values when you're down to a point source. And that is extreme unless it rips electrons off of nitrogen, oxygen, and aerosols, ionizes that plasma. That plasma absorbs the energy from the probe, from the beam, reaches temperatures and pressures like that of lightning, 25,000 Kelvin, well above anything but an O-type star, and very high electron densities. That represents in a lightning flash. We measure how much energy goes into that thing by noticing how warm it warms this flask full of atmosphere. The atmosphere clearly for Jupiter would be helium, hydrogen, helium, and probably some methane and ammonia to form these pre-biological molecules. We then, of course, sample that with a little system out here to find out how many pre-biological molecules we've built. We look at the brightness with a photometer. We look at the spectra with a spectrograph. And in this way, we can interpret what we see and realize that about 0.3% of the energy that goes into a lightning flash comes out as energy, light energy. And now we can interpret the Jovian lightning in terms of the energy delivered and the molecules produced in that atmosphere. Let's go on and talk about the Kepler mission. I'm going to give you a brief history. I joined NASA in 1962. There was a paper written by Frank Rosenblatt in 1971. Frank was an artificial intelligence investigator, a neurophysiologist, I believe. I came up with perceptron and wrote a paper saying one of the good ways to look for lightning, look for planets around other stars, is to look for the dimming of the star that occurs when the planet passes across it. He did a nice quantitative analysis of what was required, and people read his paper. He died shortly thereafter, unfortunately, in a boating accident. People read his paper, found that to be successful, it would require the development of a photometer that was at least 1,000 times better than any photometer that had ever been built, maybe 10,000 times better. And people simply said that was impossible. You couldn't do it. It was not a practical method. And they came up with other methods that showed more promise. I, on the hand, came from the can-do team on the Apollo mission and felt that with sufficient team, with a sufficient team and sufficient technology, we could build such a photometer. There was no physics that said you couldn't do it. There were enough photons, there'd been enough telescope, so you could do the job. It was a matter of developing the technology. I wrote a paper about it, pointed out, even if you had the perfect photometer, you couldn't do it from the ground because of the Earth's atmosphere. The haze, clouds, weather stopped you from finding small planets in long period orbits. You could find Jupiters in short period orbits, you weren't going to find small planets. I wrote another paper with some other colleagues, and we talked about the fact that even if you built the perfect photometer, the biggest problem you're going to face, all stars will be variable, and they will introduce a lot of noise, and that will provide some limit to what you can do. In the following years, I presented this material. I built small photometers, worked with NASA to build standards to try photometer, and tried to convince my colleagues that this would work. I was not successful. That is to say, I could do a lot with the technology, but I could never convince anybody that this was going to work. So the scientists at the Space Sciences Board reported to NASA headquarters that it might work in principle, but a clear identification by this technique appears unlikely, i.e., don't fund the effort. Like lots of other things, that really wasn't all that discouraging. They clearly didn't understand the problem so far as I was concerned. But NASA at this time came up with a new kind of mission. It had the small missions called Explorer missions, but they were too small for this kind of mission. They had the giant missions that went to Mars and landed rovers and things like that. But that was too expensive, and they only flew every 20 to 25 years. They started a new mission line called Discovery class missions. Go pick a single problem that was important, build an experiment, and they would launch experiments every couple of years. And so I thought this was perfect. I'll put together a team. I will propose to that. We did propose in 1992, and they said, your proposal is rejected. There are no detectors that could possibly give you that kind of precision. Our response, of course, was to prove that CCD detectors could give you the precision if you measure the systematic errors thoroughly and then corrected them out. So we had a chance to prepare 2 years, post 2 years later, and they said, well, you're talking about a telescope in space, and we know what they cost. They're like Hubble, they cost billions of dollars. So rejection. In 1996, we proposed again, but in the meantime, 1995 came along, and there was a tremendous jump in mankind's understanding of planets around other stars, because Didier Queloz and Michel Mayor found a Jupiter-like planet orbiting a star with a 4-day period. That was the first time people had found planets around a normal. So they found planets around a white dwarf or neutron star, and that was exciting too, but it was not quite as convincing to the community as what Mayor and Queloz had found. So we proposed in 1996, and of course they rejected. They said, well, it was great that you costed the mission in three different fashions: ground up, top down, and risk missions like the Air Force fund. And your numbers were good, but no one has ever done photometry in the way you're proposing. The standard way to do photometry of stars is you point your telescope at a star, you measure its brightness, you know the atmosphere is going to ruin that, is going to distort that because of the clouds and hazes and so on. So you compare it to a similar star in your field of view back and forth during the night, and you correct for those errors. Trouble is, you know that your comparison star might be a variable star. So you have to have a standard star in the sky at the same time. So all night long, you make the measurements between those three stars. And you can only do that for a few stars during any night, and you do it for a few weeks to get the variability. Then you take your paper results from your paper chart recorder and a ruler, and you measure the deflection of your galvanometers. And now you've done one star at a time, and you've got good photometry. You've got standard photometry. Well, what we were saying, no, we will look at 10,000 or 100,000 stars simultaneously, and we'll get a computer to do all the work. It'll analyze all the data. And so they said, well, that's a great idea. No one's ever done it. Go build an observatory and show it can be done. Now, that's quite a trick to do in 2 years so that you can propose the next time and when you don't have any funds. But you know, you got a can-do team, and we talked to people at NASA Ames, and they said, well, we'll lend you a charge card and up to $500,000, go build it. And clearly you can't build an observatory in 2 years. We went to Lick Observatory and asked them, do you have an old observatory, an old dome that we could use? And they said, sure. We have one that was built in 1870, and it hasn't been used in the last century or so. Why don't you use it? Now, of course, there's no telescope there for you. The dome leaks, it doesn't rotate, the floor is rotten, but it does have electricity and it exists. Perfect. So we fixed it up and built a little telescope and showed that we could actually see a planetary transit. And we were doing that, observing 10,000 stars simultaneously, radioing the data in an automated fashion back to Ames, where we did build a computer program that analyzed the data. So then we had the opportunity to propose in 1998. They want to do that. And they said, well, it's great that you did all those things, but your proposal's rejected. You haven't demonstrated that you can do precision photometry at 10 parts per million for something in orbit. In orbit, you don't have the telescope bolted to the ground, which can constantly point at one group of stars as it must. Instead, it's in space, and the sun will try to torque it around. You'll have reaction wheels that will hold it on target, and the reaction wheels aren't perfectly circular. The bearings aren't perfect, so it'll shake. When it shakes, it'll move the targets around, and that'll be a major source of noise. So prove it can be done, and here's $500,000 to go do it. At first, of course, I was absolutely overjoyed. We had $500,000, and I thought that was really confidence. Well, of course, I learned later it wasn't confidence. It was what they call enough rope to hang the project. We couldn't do it for $500,000. So I borrowed another $500,000, built a facility. The can-do team came together. I'll show you the results, and we were successful. So in 2000, we proposed again, and the mission was then down-selected and ultimately started development. But the year 2000 was also a great year because this was the year that the first transit discoveries were made of a planet orbiting another star. This was Tim Brown and Dave Charbonneau, who showed, yes, indeed, transit photometry really does work. And you can find extrasolar planets with it. So that was a help as well. 2009, we launched 13. The prime mission is done, and we now know most stars have Earth-sized planets around them. 2 years later, I retired, and the mission continued on doing other studies, particularly getting much more information about other stars, supernovas, and a number of other things I will talk about. I do want to mention for you, those of you who don't know what transit photometry is, it's one way of finding extrasolar planets. The obvious way is you build a big telescope and you go and look and see if there are planets around the star. That's by far the most difficult method, and it has only recently succeeded, and only for basically really early giant planets that are still forming. What's easier is to go and look at how the star itself is influenced by the presence of the planets. For example, the star will move around if a planet is orbiting it, called astrometry. People from Canada in particular did that early on, tried that. Another way is to do radial velocity. The radial velocity, of course, is what Mayor and Didi Kilo were successful at. But if you really want to find small planets, looking for the change in brightness is a much easier way of doing it. The Kepler mission. So the planet moves across the star. The signal level is just the size of the planet compared to the size of the star. That gives you the size of the planet because you know a lot about the information of the star. The orbit period tells you the orbital period of the planet with Kepler's third law and the mass and the size of the star. You can get the distance of the planet from the star. You have the temperature of the star, the size of the star, that tells you how much heat flux is on the planet. You can tell whether it's an habitable zone where the water might be present on a planet, and where you have conditions possibly conducive to the formation of life. You need to remember that this method misses almost all the planets that orbit stars, because if any of those planets don't orbit exactly in that plane, you'll miss it. So what's the probability the orbital plane will be aligned? Simply the diameter of the star to the diameter of the orbit. And for nearby planets, it's 10%. Planets that we're interested in near the habitable zone is like 0.5%. 99.5% of the stars that have planets in the habitable zone we will miss. Therefore, look at 100,000 stars, and you should find hundreds of planets, thousands of planets if you look at all the different possible orbits. And so that's the name of the game. Look at least 100,000 stars. Look without blinking so you don't miss those transits. The transits only last a few hours, and they only occur once in the orbital period. Okay, we talked about the fact that stars tend to be variable. Here's our sun. This is what our sun actually looks like in the ultralight. There's what the Earth looks like to one of the big mass ejection events, far, far greater than any size of a planet. And if it creeped across here, you would never, ever find it. But if you get rid of the ultraviolet, make that correction, get rid of the ultraviolet, now you have a visible light image of our same star, the sun. And there's this Earth compared to sunspot. So it's not too bad. It's about the size of a sunspot. Difference is the sunspots are attached to the star. The planet just zips by. So the sunspots move by in periods like 27 days. And most of the variability of the star is occurring at the rotation rate of the star. Not all of it, but much of it. But since the planet just zips by in a few hours, it sees noise that's 10,000 times less. And consequently, we can actually see little bitty planets moving across a noisy star like the sun. We know that when we talk about the precision, we're going to measure 10 parts per million precision. The stars, like the sun, has a variability we're talking about here of the order of 10 parts per million as well. But how do we know all other stars have such precision? We don't. At the time we designed the mission, no other star was known to the kind of precision required to be successful. Our assumption was that most stars were like the sun, and in fact, 2/3 of the stars should be more quiet than the sun, because our galaxy is about 9 billion years old. The sun is 3 billion years old. Stars are more quiet if they're older. When stars are young, they rotate fast, they have lots of spots, they're quite noisy, just like teenagers. After a while, they quiet down and things are much calmer. And so we're assuming most of the stars we look at are going to be at least as calm as the sun. And we'll talk about the failure of that expectation. We had to build a observatory. Here's what it looks like. Here's the dome, built in 1870. The electric motor that drove it was built in 1870 also, and so it didn't function. But, human beings have shoulders, and that's what shoulders are for. You could push the dome around. You don't really have to have somebody else do it for you. Here's the homemade telescope with an aerial reconnaissance lens from World War II. Pedestal we built, and here's what our data look like. Here's HD 29458. We didn't find that planet. We knew where to look, but we see, here's the prediction, here's our measurement. Beautiful, beautiful agreement, even at air mass equal 4 before the star set. And this was proving we could certainly find planets with the required precision. We had a mascot here. We called our little mascot Spock, because Spock had very unusual eating habits. He liked to eat wires, and he liked to eat little hoses that made the telescope work. So when he didn't show up, we assumed that there was some fat, happy snake, and we were happy too. But in any case, he was our mascot for many nights. The next thing we had to do was build a facility that could show 10 parts per million photometry with the kind of noise that would occur from stars ninth magnitude, 12th magnitude stars, and so on. Here is our facility. It's the size of Dr. Who's phone booth, about 3 meters high, 1.5 meters across. We've got a light source here, scattering source here, a plate here with thousands of laser drilled holes that represent stars of various brightnesses and various closeness to one another. The light comes up through this column. There's a telescope here, CCD, and a device that shakes the telescope with the kind of power spectrum that's representative that of the actual telescope that would be built. Here's some of our results. Here is the noise appropriate for our telescope and for the star of the brightness, and we can see a planet with the same area as the Earth shows a very, very clear detection. Here's 2 more, no problem. Here we go to a 12th magnitude star, some 20 times fainter. And now a 1 area dip can be seen, but you're going to have to look for it. You're going to have to see several. Something that's 1.5 times the size, in other words, twice the area, is going to be clear. So basically, we're demonstrating we can indeed find planets with the kind of noise that these stars have. And you can see the noise here is quite a bit higher than here. So we got the go-ahead. We built the system. Here's the launch. The spacecraft is about the same size of a VW bus. It's in this pod here. This is a Delta II rocket, a very dependable rocket, 3-stage with some strap-on boosters. And if you remember the Delta II rocket, it was noted for the fact that the Air Force used it to launch our GPS satellites, global positioning satellites. They were launched with this rocket. Well, they had a failure. And so the Air Force looked at the design of this rocket and made some changes. And said, okay, we've got the changes made. It'll probably work. But we're not going to launch on it. We're going to make Kepler launch on it. So they pushed ahead our schedule and said, ready or not, we're going to launch your vehicle. And so they did. They launched it on March 6th. That was certainly not our hoped for date. We were, I think, going to launch on April 10th. So they launched into heliocentric orbit, worked like a charm, and we're now in an orbit around the sun 53 weeks. And that's especially important. The spacecraft does not orbit the Earth, which means it's never close to the Earth. It points away from the sun 24 hours a day, 365 days a year. It never has a day-night cycle. It always sees darkness, so it can always look at the same group of stars constantly, day and night, and send back pictures back of this group of stars because it never moves. It always looks at the same group of stars in its field of view. It was designed as the most boring mission ever flown. And it succeeded. It just found transit after transit, 1,000 stars after 1,000 stars. So, let's go on. One of the things that it is, it looks constantly at these 170,000 stars, essentially without blinking. It does send the data back and so it stops for briefly every month or two. But it learns a huge amount about the stars because most of the data is about the stars. So I'm going to show you some of the wonderful things it found. We thought the sun would be the most quiet of the stars, like the sun, same size, same mass. And so here was lots of noise. It was what we measured, what we knew for the sun. About 12 parts per million, 10 parts per million, depending on the part of the cycle. And we expected most of the stars would have less noise. And here is the number of stars we found for different noise levels. We found a few number of stars, 20, 50, 100, that were less noisy than the sun. But we found the majority of the stars were much, much more variable than the sun. We have no explanation. It's a mystery. It's a puzzle. Another puzzle for the student. In any case, of course, what that meant was we had our burst noise sources, and in reality, of course, our noise was louder than expected, and our total was about 30 instead of 20. What that meant, the signal-noise ratio was greater than expected, and that meant we didn't see as many small planets, particularly long-period orbits, as we'd hoped. We will have to correct for that. Here's one of the stars that we looked at, one of several actually, and we can see we've got the intensity being measured, and it sees jiggles around, little bumps, but there's a dip, a regular dip here. And there's another bigger dip that's regular as well. If you fold the data, you put all of these together and average them, what you see is a transit. Here we say the average is 1, and we can see all the data come along here, and we see the star get dimmer nice smoothly as the object moves across the limb of the star, because the limb of the star is darker than the center, and then it goes across the center and gets the maximum dip. Comes back up again. This is a beautiful transit. And it shows you, since you know the size of the star, that this thing is something smaller than Jupiter. But what's interesting is this big dip. The big dip isn't smooth like that. It's perfectly flat across the bottom, and it's a very steep change. This is indicating that the object, when it crossed the star, blocked a small amount of light, but went around the back of the star was blocking much more light. So the object was much brighter per unit surface area than the star we were looking at. What could that be? Certainly what we found, the star's temperature was very high, probably a B star, but the companion was 12,000 Kelvin. So basically what we were finding was a surprisingly large white dwarf. And we found a number of those. So a lot of interesting stars for which we have data. Now we know that when a planet goes by, it blocks the star and the star gets dimmer. This star got brighter. So we go along here and we see this big brightness jump. Now you wouldn't see this with a ground-based telescope because the change is only 6 parts per thousand. Very hard to find. But we see it very, very clearly, and we see the oscillations that lead up to the spike and the following oscillations. Again, it repeats very evenly, and so you can add these up, and what you see is this very regular oscillations, this big jump, and it comes back down again. How can the star get brighter? Well, if there was some gravitational focusing, if there was a black hole, a small black hole in front of it, maybe that's what we would see. So, of course, we had made some observations with X-ray telescopes, and we found, no, that wasn't it. What we had, in fact, were 2 stars, but they were orbiting each other. But the orbit wasn't circular. The orbit was nearly linear. So these 2 stars would go out to a huge distance, stop, come screaming toward each other, and when they did, they nearly struck one another. So you can see here's the 2 stars far apart, they're nice and spherical. Here, they're a little bit closer, they're a little bit oblate. Here, they're quite a bit oblate, they're getting closer. Here, they're much closer, they're quite oblate. Here, they're almost hitting each other. They're very, very elliptical. And so the area is expanded in our field of view, and so we see the brightening. And then, of course, they pass each other and they oscillate. The upper atmospheres oscillate. And we can learn quite a bit from that the oscillation of those stars. Again, we saw quite a number of these stars in different orientations. We had a group on our team that did astroseismology. Astroseismology teaches you so much about the interior structure of stars and their age. So we had an entire team of people, an entire institute of team that looked at this data, basically. And what we see here are the acoustic oscillations, the variations in brightness of stars as we looked at them. And we're plotting the frequency, the power spectrum. How noisy is it as a function of frequency? Here's a young star here, and it has lots of noise at these lower frequencies. This are from granulation noise. The stars, like the sun, have spots, and these are plumes of very hot plasma that come pouring upward, overflow where we're supposed to stop, and fall back down the star, and they shake the atmosphere of the star, and so you see that granulation noise. But they also cause resonance, so it's like hitting a drum. The drum resonates and shows you a bunch of frequencies, these very nicely delineated frequencies. These frequencies have nice big constant spacings. These are called large spacings. If you look closely, there is a narrow spacing. There's another narrow spacing. So there's 2 spacings that we're seeing here, wide spacings, narrow spacings. The other thing we're noting is here is where the maximum is. As the star gets older, it begins to fill out. It's like a human being, it fills out, and it gets slower. And so these oscillations are dropping in frequency and moving to lower frequency stars much older. Now we're beginning to see not only oscillations from the atmosphere that go through the planet and tell you about the structure of the planet, but structure of the star. But the star is now going through the finishing parts of burning its hydrogen. Burn the hydrogen in the core, it's now burning hydrogen in a shell that's expanding outward. And it's dumping that hydrogen, burnt hydrogen becomes helium, dumps the helium in the core becomes denser and heavier, and it begins to oscillate. And we can see the changes in the spectrum. We can see the gravity waves of the core begin to appear. And finally, the core gets so dense that it ignites, shrinks and ignites. So all this is happening. All these things are happening in red dwarf stars. And so they're expanded, they're giant stars, but you can't see inside them unless you can see these waves. And so this data was wonderful data that was useful to the people who were trying to understand what happens in a star that evolves from hydrogen burning to helium burning. Again, look at this. We can tell the age of the star from where these spectra are. We can tell the mass of the star. We can tell so much about the star from this data. And that was very useful in terms of understanding what we were looking at when we were finding planets. One of the things we can do, and I love talking about stars, is wide spacing versus narrow spacing. Let's plot wide spacing versus narrow spacing. When we plot that for various masses of stars between 1 and 2 mass of the sun, we see a bunch fall right along here. These are hydrogen burning stars. Now the narrowing period has gone up, and we're seeing it with the same mass range, much different spacings. And this is telling us these stars are helium burning. And we can tell that just from that those oscillations. Okay, it's time to move on and talk about planets. And I'm going to talk. Some of these figures are early figures, but they are so expressive. They're so good explanations of what we found that I'm going to use them. First thing we do, we look at what we found. We found 800 Earth-sized planets or candidates, 1,200 planets that were somewhat bigger than the Earth, but smaller than Neptune, somewhere in the median. 1,500 Neptune-sized, 260 Jupiter, 50 planets larger than Jupiter. That's sort of a surprise. How do we have planets bigger than Jupiter? Jupiter is the size of a small star. A real puzzle, but we do find a fair number of them. The trick to remember is it's easy to find big planets, hard to find small ones. That means we've missed a lot of small planets. There must be a lot more small planets than big planets. So what we see, the sample distribution. What we want, what's out there, is the parent distribution. We have to correct the sample for the parent. And when we do that, we correct from various biases, what we find is the number of small planets gets larger and larger and larger. We know that about half the stars that we look at have planets about the size of the Earth, another 25%, 1.5 times as big, and so on. So what this data is showing is on average, most of the stars in our galaxy have a planet about Earth-sized. Not necessarily in the habitable zone, but an Earth-sized planet. This is early data, and that number tends to be thought more likely to be 2 Earth-sized planets around the stars. Now, there are 300 billion planets in our galaxy, and there are more planets than stars. There must be over 300 billion planets. So our galaxy has a huge number of planets, and we can talk about that implication. One of the planets that we found in the habitable zone was this planet. It was a planet between the size of Earth and Neptune. We find a lot of these. This one is in the habitable zone. Now, it could be that it's a really massive super Earth with huge gravity, because of course the core would be very, very condensed in such a planet. Or it could be a mini Neptune, where it's got a very extended core around an atmosphere around a small core. the theoreticians tell you, well, it could be something else. It could be, in fact, a water planet, a planet that had a core of water or ice. And on the surface in the habitable zone, it's going to be covered with water, an ocean planet. Well, it's in the habitable zone, the ocean is warm. Warm water evaporates. It evaporates into its atmosphere. This planet must have a water atmosphere. What else is common in our solar system other than water? Nitrogen, carbon dioxide. So probably it's because other planets in the solar system have that, and you see that among the galaxies, inside our galaxy. So this atmosphere probably is nitrogen and water vapor. That's exactly the kind of atmosphere Earth had before life arose. After all, it's life that makes the oxygen. So does this planet have life? Are there fishes swimming in that ocean? We don't know. And Kepler was not designed to answer that question. It was only designed to get statistics for more powerful missions that would look at planets like this and tell us about the atmospheres and whether there's life. Well, one of the things we, of course, want to hunt for is Luke Skywalker's home. We know that Luke Skywalker lived on a planet in a habitable zone and it orbited a binary star. Well, there are a lot of binary stars out there. In fact, if you ever look out at night and wish upon a star, about half the time you don't wish upon a star, you wish upon a double star, because binary stars are so frequent. Now, I don't know whether wishing upon a binary star gives you twice the probability of getting your wish or not, but there are a lot of stars out there, and we'd like to know, do they have planets? The answer is yes, indeed. Here's an example. A binary star, a planet in the habitable zone around that star. Is it Luke Skywalker's home? No, it's not. It's too big. It's a gas giant or a Neptune-sized planet. So we're going to have to keep hunting, but we certainly do find planets around binary stars. Our deepest interest, of course, is to find planets the size of the Earth. Are we finding them? The answer is yes, we are. But we're finding many of these around small stars, because small red dwarfs are much more common in our galaxy than G dwarfs like our sun. And here's an example. And so what we see is the habitable zone in green. That's shown here. The habitable zone, it was the temperature of that planet. It's going to be just right, the Goldilocks zone. If you move the planet inward from there, the planet's too hot. The oceans boil. Move it too far out, it's cold, like Pluto. You're never going to have life. So if it's in here, there's a possibility that you have water on the planet, you might have life. And of course, this zone is much smaller than ours because our star is much bigger than this star. This star is probably a half to a quarter that of the sun. So you have to be in much closer. You have to be much cozier to be in a habitable zone. Unfortunately, that means you also are likely to find some UV events and things like that, X-ray events that you might have to learn how to get around. So we are finding planets and in the habitable zone. I'm going to skip this. I don't think we have time. We're running out of time. Here is one of the more interesting planetary systems that we found, several of them actually. What we have here is the semi-metric axis. That's the distance from the planet to the star. It's a compressed scale, it's a logarithmic scale. And you can see here's the Venus and Earth and Mars, and these big giant planets in our solar system, Jupiter and Saturn, Uranus and Neptune. And many of the planetary systems we found are much closer to their star, but generally much bigger planets. These are planets almost certainly that have a gaseous hydrogen helium atmosphere around them. They're just too big to be solid planets. But this is a planetary system we found that has 5 small planets. The planets are close to their star. The star is named Kepler 444. They're so close, they're so small, they must be rocky planets. So we've got rocky planets. And this star, Kepler 444, we can get the age for. We can get it a number of different ways, but we know the age of that star. It's 6 billion years earlier than the sun. If you lived on that planet when they were being formed, and you look up at the nighttime sky, you would not see the Milky Way. That's because there was no Milky Way. This was the time hydrogen and helium were condensing to form the stars that would form the Milky Way. So even at the beginning of our galaxy, rocky planets were being formed. And after that, as time went on, year after year, more rocky planets. So if you had life being evolved over that period of time before the formation of the Earth, before the formation of the sun, those life forms might be some 6 billion years in advance of our own. Not in advance of 100,000 years or say 10 million years, like difference between us and dinosaurs, but billions of years more advanced. So as we explore space, we may come across some very interesting life forms. Okay, so we need to finish up. What have we learned? We've learned that most stars have planets, something we didn't know before Kepler. Most Earth-sized systems are quite common. We have billions of Earth-sized planets in the habitable zone. And that brings up a question that was asked by Enrico Fermi many years ago. If there's life in our galaxy, why hasn't it contacted us? Well, the answer was easy. There's not any planets out there that have life. There are no planets out there. Earth is unusual. We know the answer is not that anymore. Now we know there are billions of Earths, billions of them in a habitable zone. So the answer must be something different. Our telescopes have operated, radio telescopes, for 30 years. They've picked up no signals from any life form. Why haven't they heard anything from life out there? Well, there's a lot of possibilities. There's a book written on it, in fact. One of the possibilities is that our assumption that as soon as you've got a planet with it's habitable, it's got water vapor, it's the right temperature, life spontaneously forms. That's an assumption. Maybe that's not true. Maybe it only happens very rarely, once in 100 billion times. We're alone in the galaxy. That's a possibility. Another assumption is, no, life does form very quickly, but it only evolves like it did on Earth to the stage we have bacteria. That's life. That covers the Earth. Then there has to be a jump from bacteria to a eukaryote. You have single-celled organisms now. That took a long time. What if that never happens? They couldn't contact us if they were paramecium. If you finally get past the Precambrian and the Cambrian, you start forming multiple cell organisms. You generate higher animals. You generate really advanced creatures like dinosaurs. They ruled and covered the Earth for 50 million years. But they never contacted us. They never said hello. And that's because they never evolved a technological civilization. So you might evolve bacteria, planets, you might have planets that are paramecium, there might be planets with dinosaurs, with no technology. Maybe those are the answers, the way we've heard from no one. On the other hand, you could assume that it's not true. All of these things evolve very quickly once you have such planets. You build a technology civilization, and it destroys itself. It's unstable. Now, no one knows the answer to that. But we do know there are billions of Earth-sized planets in the habitable zone. So there's another exercise for the student. Find out whether those planets have life. Now, what is the next step in the search for life for our galaxy? Find the closest planets so you can examine them more thoroughly. You can examine their atmospheres. Determine if the planets have an atmosphere. Finding a planet, like the moon's almost planet-sized, it's in a habitable zone. Without an atmosphere, you can bet it doesn't have any life. And determine whether that atmosphere has any gases that would tell you the possibility of life. Possibly oxygen, methane, possibly chlorofluoromethanes, like you use in refrigerators. That would tell you there was life. Okay, so missions that are being designed, being flown to continue the search for life on Earth include the new ground-based telescopes that have the capability of looking at these extrasolar planets. Parnell University Observatory, for example, has the very large telescope, the European Very Large Telescope. You know, it's one of the biggest ever built. It has the Atacama Large Millimeter Array, which is already seeing the disks that produce the planets that orbit the stars. And so they're already finding this data. The Plato mission will launch in a few years and tell us more about nearby stars. JWST will actually have the capability of looking at some of the atmospheres, certainly of the bigger planets, maybe a few of the smaller planets. WFIRST will fly. And you say, well, WFIRST is not going to fly in nearby planets. It's going to find very, very far away planets and planets quite far from their stars generally. Well, that's right. It'll find planets like Jupiter, Saturn, you know, places where they belong, with orbital periods of the order of 12 years or 30 years. And that means those planets in our solar system helped control the formation of Earth and Mars when our planetary system was built. And so we want to know about those Jupiters. Jupiter may have protected the Earth from the asteroids that destroyed the dinosaurs. We're rather happy that the dinosaurs got destroyed, but we wouldn't be enthusiastic about having them destroy us a more advanced life form could form. So we have LUVOIR and HABEX, which would be even bigger space-based telescopes that will fly and allow us to look at small planets and their atmospheres and the composition of those atmospheres. So thank you for your attention.
Wonderful. Thank you very much, William, for a great talk. We have quite some activity here in the Q&A, and I would like, I think, to open up first the discussion to the panel members, if there are any questions.
Yeah, it's Gordon Walker here. I'd just like to follow up on that after that wonderful talk, that you had the courage of your convictions and they carried through. I think there's a very strong case for a high-resolution telescope dedicated to high-resolution spectroscopy of just those things which block out the light from the stars, that is the Earth's atmosphere, and to follow up on all of those things that you just talked about, the signatures of in atmospheres of life-generated gases. It's going to be an exciting future.
Yes, spectroscopy is such an enormous key to understanding what we're seeing. And I certainly hope that there's maybe not many more than one such telescope being built, both in space and on the ground.
So a little bit related to this, of course, there is always the worry of having these biosignatures in part being sourced by some geological processes. So how, there's actually a question here by Douglas Alves in the Q&A that points into that direction, that says, is there any combination of biosignatures that we can apply to be, you know, let's say 99.999% sure that there is something living on this planet?
Yes, there certainly is. I think what he's getting at, of course, is that if you find oxygen, that doesn't prove there's life. I think it's sort of indicative of life, but it doesn't prove it. And this is something you really want to prove. You don't want speculation. You want to know what the answers are. There's oxygen on Venus, and Venus certainly is not going to have any life. It's the inside of a pizza oven with no water. But one of the things you can look for that is a better proof is chlorofluoromethanes. Those are the gases that humans generate for refrigeration systems. Nature doesn't make those gases, and yet they're extremely useful in the earth for human beings. So it would certainly indicate you have life and that you in fact have intelligent life. I don't know, other spectra, it's trickier, but I think there are other, you know, Gordon is talking about how important spectra is to the future of understanding. And when you use it, you can look, for example, does the planet turn green seasonally, for example? That's probably meaning that, you know, you've got a summertime life springing up, and later on you've got a fall and a winter, and it disappears. So you, from photometry, from spectroscopy, you can get indicators, but those are not necessarily proof. You're really going to have to use a lot of effort to prove there's life, and in particular, there's intelligent life there.
Right. So in essence, so what we would like to do is to combine some kind of biosignature with some kind of technosignature in the end, right? To be 100% sure that there is something crawling and producing something on the surface of the planet.
Well, you know, there's an entrepreneur who's building a starship and expects to go to one of the nearby stars. So that's another way of doing it. You just have to be patient.
Very sure. Giuseppe has his hand raised. Giuseppe, go ahead, please.
Yeah, thank you, Thomas. Thank you, William, for your passionate talk. And I have a question. I had a question in mind. I want to recall also a question from the Q&A by David Katzenel and his discussion with Jose Rines. Kepler, with Kepler, the demography of exoplanets literally exploded. And it is certainly a very efficient technique, this one, for discovering exoplanets. What's your feeling about, about microlensing, for example?
Microlensing is wonderful. They're finding planets, and they're looking at very far away stars. So they're sampling not just the local star group, because maybe the local star group is the explanation of why our sun is so much quieter, because a lot of the local stars are young. So WFIRST will be doing that. Microlensing, hey, it's a wonderful technique, and we need every technique if we're going to understand what's going on around us in our galaxy. So it's a marvelous system.
So we have another question that's been very highly ranked in the Q&A by Cynthia Olvera. So it's in Spanish, but I can give you a translation. Could the number of planets be related to the type of star that they're orbiting?
That's a good question, because people have wondered, you know, you have really small stars, you have really big stars, you have hot stars, cool stars. What is the relation? We haven't seen enough data that clarifies, gives you a good answer to that. But we do see a substantial number of planets around the smallest stars. We see a fair number around the bigger stars. We don't see enough of the really hot big stars to give you good statistics. But so far as we know, we don't see a strong correlation. If people were to bet that there was a correlation, they would bet there are more planets around small stars than they are around big stars. But I think that is pretty premature, because it's easier to see planets around small stars than it is around big stars.
We have a question from Christian in the panel.
Christian, yeah, congratulations, Bill, for Kepler and your life achievements. So my question is more about Kepler and the project. So if you had the ability to, go back in time at the beginning of the project, and in light of everything we know now about the field, would you change anything about Kepler or its mission?
One of the things that was really difficult was that when you develop the mission and you look at missions that have flown before, one of the things that really is damaging to a mission is to not fund it as accepted in the proposal. It causes all sorts of problems. And for us, when they did that, when they interrupted the mission development, it caused us to go way over budget, and it meant that some of the testing that we should have done was not done. And consequently, some of the detectors were much noisier than they should have been, for example. So that to me was one of the big difficulties. I keep pointing out to people, it's a rather inexpensive mission, because we know how to build this. You don't have to go and prove that, for example. And if you want to say, I want to find how frequent Earths are around stars, say, like the sun, in Mars orbit, or I want stars that are, say, F-dwarfs, with perfectly reasonable stars. You need to fly another Kepler. You need to find Kepler with reaction wheels that last longer. Just build a bunch of extra wheels and bolt them on. So I would have changed I was just a little bit disappointed that we couldn't have a better funding schedule and do more of the testing we all knew needed to be done before we flew that mission.
So we have another question from the Q&A. Can you give any words about whether we're close to detecting exomoons or planets with rings around them?
We'd all like to do that. We'd all like to find moons around these planets and rings and so on. And again, one of the ways you would find them is you would, for example, if there was a moon, you would see a little dip before you saw the planetary transit, or the dip might occur afterwards. And if you see enough dips, and you might be able to get the orbital period, the size of the dip would tell you the size of the moon. And if you couldn't do that, you might notice that the noise on that star changed about the time the transit occurred. So people are looking. There was a group that felt they had looked at the data and found moons around a number of stars. But ultimately, when they examined the data very carefully, they decided no, there was not enough signal noise to say they were moons. So people are looking for both the rings and the moons. I think it's probably easier to find the moons, but if you say, what about something like, what if two planets were to crash into each other and all that debris were to be spread around in a ring? Well, we see something like that might be just exactly that. I didn't show it, it didn't, but we have seen something that looks like a huge structure. Some people thought, well, maybe it's an artificial structure, a Dyson sphere or something. But in any case, we do see some strange things out there, and it might be that a more capable mission could follow up and get more information. But right now, we're doing the best we can with what we have.
So we have another question.
Can I make a quick comment? Would you not also expect to see timing errors if there's a satellite around a transiting planet?
Thank you. It's a nice setup question. One of the wonderful things that have happened during the mission is we've had some theoreticians who said, well, when the planets go around, you've got two planets going around the same star, they affect each other, they gravitationally affect each other. And there was an astronomer hired once upon a time. His name was Kepler. He was hired by Tycho Brahe, and Tycho Brahe was trying to come up with a good planetary system, and he kept finding that Mars didn't move through the sky the right way. It got there too early, got there too late. How would you explain that? And of course, that timing change that occurs is something the theoreticians, the observers have used with the Kepler data to detect planets that we don't see and to get the masses of the planets that we do see. It's an extremely effective technique. It is a wonderful contribution to all missions that do transit photometry. It's extremely hard to get the mass any other way unless it's a massive planet. For Earth mass planets and so on, we've been successful at doing that. There have been time I would have shown some figures, but Gordon, thank you for the question. It is a wonderful technique that young people have come and added to the mission capability.
So we have another highly ranked question asking, how are exoplanets named and how unique are they from each other?
How are the Kepler planets named? If you look at star catalogs, they generally name the stars for a certain region, a certain person. The Draper, we have the Henry Draper catalog, HD catalog for stars, and so on. So we've got to do something like that. We have to do something like that for all the stars, 170,000 stars we're going to look at. Actually, we looked at 190,000. Most of those are so dim, they're not in any catalog. So the science team had to get together and decide, how are we going to name these things? And people said, well, we could name them like you name quasars and so on, with the coordinates of these things, but just a stack of numbers. And nobody liked that. And we couldn't come in. We had a science team meeting. Everybody's discussing this. And I knew the solution. I said, okay, we're going to name each of these Borucki 1, Borucki 2, Borucki 3. And immediately we had 100 good ideas. And they said, let's name it after Kepler. Kepler 1, Kepler. Hey, that's how we did it. They're just named in the order that we found them. And when you look at the planet names, so we're going to find, say, Kepler 10. That'd be Kepler, not 10A, because the A refers to the star. 10B is going to be a planet orbiting it, and 10C and so on. And so basically we named them in terms of when we found them, or if we named them together. Let's say we on Kepler 62, for example, we found a bunch of planets. We were able to name them from the innermost to the outermost, which is what we would have preferred. But sometimes they're not named innermost to outermost. And of course, people find, Kepler, after all, didn't find all the planets. They're students and people, citizen students find planets that we missed. And so those get a number like Kepler D or F or G or something. But that's how they're named. Something simple and unfortunately not after Borucki.
That's a pity. Okay, we have a question from Viviana on the panel.
Yes, thank you, William, for that fantastic talk. I actually had a question about planets around binary system or triple systems or even more complicated systems. What would be the most complex planetary system that Kepler found? Like how many planets around maybe how many stars?
Well, as the systems get more complex, it gets much more difficult to recognize what you're seeing. If you say, let's just take a double star, we want to see a planet orbit it. It's maybe 1,000 times more difficult than one planet around a star or many planets around a star, because those around a single star, the planet's repetition rates are generally extremely accurate, precise. They see the orbit is exactly the same, the duration is exactly the same. There's a little difference when they interact with one another, but generally it's quite good. If you say, no, I'm going to have a planet around two stars, when the transit occurs depends on the phase of where the two stars are. You could have the two stars lined up, planet goes across, you see one transit. Or you could have the two stars like this, and you see two transits. Or as the stars are moving fast, because they move faster than outer orbit, you can see three transits. A computer doesn't know how on earth to look for something that's non-periodic. So the fact that there may be lots of planets around double stars or triple stars or quadruple stars, and there are a fair number of triple stars and quadruple stars out there, means whatever we find is a small fraction of what must be out there. And we do find planets around triple stars, and we found planets around quadruple stars at this point. I think we've only found one planet on a quadruple star. I don't remember what we found around a triple star. And when you think about a triple star for a moment, you could have two inner stars and a faraway star from that's orbiting a two. And that's like the, God, what is this? This nearest star to us is Cis, not Cygnus, it's whatever. In any case, that's a double star with another star further away. And it could have a planet orbiting that faraway star. Or it could have planets orbiting the two inner stars. Or it could have planets around one of the two. I mean, there's all sorts of things that could happen when you have multiple star systems. And so it makes it very difficult to actually look through the data and figure out what on earth what you're seeing. Are you seeing any of these situations? And quite often the discoveries did not come from computer searches. It came from searches by people who just looked again and again at the data by eye.
Okay, we have another question from the panel from Christian.
Yes, you touched a little bit at the beginning about what it's going to take for humanity or us to be convinced that we found life or a habitable planet or an atmosphere like Earth in the atmosphere on another planet. But now the question is, what do you think? How long does it going to take for us to get that proof? And what's going to take? New observatories, or what was current plan, or something even beyond these observatories?
But you're asking the wrong person. Look at all the young people here. They're the ones who decide that. They're going to be controlling that. They're going to control the funds. They'll be in positions of power. I have no idea. It's up to them.
And I pick up on one point you were saying, and also on Christian's point. Surely we have the solar system to look at. Venus was probably habitable at one time before they run away. Greenhouse effect. We know we've had life on Earth. Was there life on Mars? We're going to find that out pretty soon, I think. And we've got at least 2 satellites of the giant planets where
Yes.
all of those are going to say whether or not life does arise fairly spontaneously on, they don't even have to be in the green zone. They can be satellites with an internal energy source. So you and I should live long enough to know, Bill.
I'm certainly hoping to do that. And that's an excellent point, that we do have a lot of planets or planetary bodies where life might exist. And if we do the explorations in the coming few years, we might find the answer is yes, life tends to form rather readily. And that would be absolutely astounding. We would use that to extrapolate to all these other planets. On the other hand, if we looked at Mars, saw no fossils, and we went to Enceladus and what was the other one, and found no evidence of life there either, that would be an ill omen.
So we've had a couple of questions from Eduardo de la Fuente. He's commented that we've been sending out radio signals into the universe for about a century, and we've been listening for radio signals from other civilizations for the last 30 years. Since we haven't heard anything yet, does this mean that there's no advanced civilizations within the 15 to 30 light year range?
Well, Jill Charter always likes to say that the radio searches that we've done up to now, they've been very serious. And as you're talking about out to 30 light years, that might be quite a reasonable thing to think about. But we're basically dipping a little cup in the ocean and asking, are there any whales in it or any fish in it? And the answer is probably no. Doesn't prove there are not any fish or any whales out in the ocean. So I don't know the answer to that. I suspect that that if there was life that was so frequent, we might very well have heard something, because the techniques that we have today are pretty sensitive to signals from planets that were within 30 light years from us. So it's a little bit surprising we haven't heard anything if life, technological civilizations are frequent.
And I have a connected question from my own interest. I mean, if we do hear from a civilization, how likely is it that we will actually respond and announce our own presence?
Yeah. We could say hello, and that'd be very friendly. And they could say, hello, there's a bomb on its way to see you. The people have to decide exactly, as a civilization, as a species, how do we respond? I don't know what the answer is. I guess there are some people who've already used giant telescope time to send messages out. I'm not sure that was wise.
Yes, there was the Arecibo message going towards a star cluster.
Yeah. So
there is another question here in the Q&A, which is sort of related to the discussion before about habitability. And I have also my own question that I wanted to ask you. Where do you think life beyond Earth is actually most likely? And that relates a little bit to the habitability, basically running through a planetary system in time. And you have to place actually the correct, let's say, planet or exomoon in the right spot for the right amount of time around the right star. right, in the right orbit around the center of the galaxy to arrive at some, let's say, statistical likelihood to find the biosphere. So where do you think that place is?
Well, you want to keep in mind that statistics generally is you did a bunch of observations and some phenomena occurred X of the total number of times. Good statistics. Since we have no value for X, statistics makes no sense. We have no statistics. Well, if you don't have statistics, what do you have? The answer is speculation. Speculation by somebody who's an astronomer or somebody that divines the innards of crows is about of equal worth.
Okay, so we have another question at the top of the Q&A. Again, it's from Claudio Manera and it's in Spanish, so I'll give the translation. So the habitable zone is dependent on the type of the star, and the timescale that the stars will be, that the planets will lie within this habitable zone may vary. I mean, what's the probability that all stars have habitable zones where planets will stay for long enough for life to form? Sorry, my translation is a bit dodgy.
Okay, I understand the question. It's a good question. It's an important question. And people have thought very carefully about it. Basically, the big bright stars burn up very quickly. In terms of our lifetime, of course, it's not quick, but they can burn up in 100 million years. We think it took life of the order of 1 billion years to evolve. You can argue it's 500 million or 2 billion, whatever you'd like, but it's of the order, of hundreds of millions, billions of years. And these really big bright stars burn up too quickly. So you don't think you're going to have life in them, habitable zone or habitable zone. As the stars get old, get less massive, they live longer. If you take a star as massive as the sun, which is quite light compared to some of the more massive stars, it lives for something of the order of 15 billion years. So for a period of a few billion years, it will have the right conditions for the orbit it exists in, for it to be habitable. At the end of that time, it's too hot. The star is lit up, it's too hot to have life there. So as Thomas was getting at, you'd better have been able to move to Mars and build yourself a nice atmosphere and lots of pretty lakes to sail on, or further. By the time you get to the small, really frequent planets, the K dwarfs and so on, they live for hundreds of billions of years, and their habitable zone stays the same for a long time. The difficulty is that it wasn't habitable early on. Early on, the star was very bright. It had a huge amount of X-rays and gamma rays, and it was sterilizing all the life that might exist as the planet was young. Is that a good place? Could life have been there? Did it start under a rock away from the gamma rays and then crawl out from under the rock and evolve into technical civilization? There's just a way of knowing. Basically, it does depend, life probably does depend on the star type. And we certainly don't expect to see life around the really hot, short-lived stars. So it doesn't make sense to go look there, but certainly looking around the nearby stars, the K's dwarfs, G dwarfs, and the G dwarfs, K dwarfs, the N dwarfs. Stars are more or less like our own. I think that is where we should look. And certainly F dwarfs are not that much different than the sun. If we can do that, that would be great also.
So we have 2 more questions from the panel to finish up. So let's go to Melissa first.
Yes, thank you for the very nice talk. At the end, you mentioned some of the upcoming space missions. What discoveries do you expect or hope for from those missions that you're most excited about?
We would like to understand life throughout the universe. Civilizations, the planets, all these things. All we get right now with our technology are little tiny clues. But we need every one of those clues. Well, there was a question about W first and the fact that it's going to look, with microlensing and things like that. It's going to find planets that are generally quite a ways out of the habitable zone. And I pointed out, but that's going to be valuable too. So if you say, well, no, I'm going to look with the Atacama Large Millimeter Array, am I going to see planets? Probably not. But I'm going to see the disks that form the planets. So we're understanding more about how the planets get built. So every one of these things is extremely valuable. Looking at the stars, what have we found? We found something about what's going to happen to our own star. It will become a red giant sometime. It will start burning helium sometime. So we want all the clues, and every one of the experiments that we have none of them is going to give you the answer. You need every clue, and then you need some sort of rationale to bring it together and say, this probably implies X. And then try to check those assumptions. And then what I say, one of the big assumptions these days is that if you got a habitable planet, a habitable zone, you're going to have life. That may not all be true.
So we'll take one final question from Viviana.
Thank you, Evelyn. Yeah, I was remembering what you show, the path of Kepler, and it's really impressive to see how hard it is to develop and actually launch one of these missions. So I was wondering if you had any words of wisdom for the young scientists on how not to give up when you have an idea like this, because it takes a long time.
Well, my advice really is, as you pick your career, to pick some topic, some area that really is important, because you're going to spend a good fraction of your entire life. You only get one life. Spend it on something worthwhile. I don't think I'd like to be a banker, for example. I want to know about biology or stars, or something worth spending the effort on. Because if you're going to really make progress, you're going to compete with a lot of other people. So you're going to have to work extremely hard, be extremely perseverant. My boss said, now that the mission succeeded, people say, Bill, you were really perseverant. But it's just a different view. You really have to pick something important, something you believe in, and work very hard to make it work.
Thank you very much.
So,
and don't expect to get promoted. It doesn't happen.
Yeah, that's very good advice. Perseverance is really key.
You got to work for a place like NASA, where it's hard to fire you because you're a government employee.
That's a good trick to have too, yes. Wonderful. Okay, so I think we're going to wrap this up. Thank you very much, William, for a wonderful talk. And thank you very much to all our panel members for being here and asking excellent questions. Thank you all for joining us today. And just want to say that the series, of course, will be published on our Astrofísica YouTube channel. So we had a little bit of audio issues today, but I think we're gonna fix that in the post. And both channels, the English channel and the Spanish channel, will be available. And of course, the video stream will have also higher quality than on the live stream.
And I'd like to add my thanks to everyone. I enjoyed the questions. It was nice that people showed up. And thank you so much for setting this up, Thomas and Evelyn and Patricio. And I think I've forgotten somebody, but at least I picked a few. Thank you.
Thank you. Thank you. Thanks to everyone. This is a team effort, and we are really trying to bring science to the public. So our next scheduled talk, well, we actually have two really cool talks coming up in July. One is by Jocelyn Bell Burnell, the discoverer of pulsars, and the other one will be by Jill Tarter. So stay tuned for the announcements, and yeah, there is nothing left to say than thanking you all again very much, and hope to see you very soon on this channel. Take care, everyone.